Hello, and welcome to class 11 of Physics 350. This class is on polarization, which involves the response of a material to an applied electric field. We've been talking about electric fields generated by materials. Now we're going to talk about the response of materials to an electric field. We're not going to do as much on polarization and the response of materials as usual. That's to make room for the projects that you guys will be doing later in the semester. But we'll do a little bit in this class just to get your feet wet into it. So this is section 4.1. So polarization, remember from the last lecture on the multipole expansion that we have a dipole moment, and the dipole moment is given in equation form by the sum over a number of charges of the charge times the charge distance of the charge from the origin. So for example, for these two charges here, minus q and plus q separated by a distance d, the dipole would just be d times q over 2 plus d minus q minus d over 2. So qd, q times d. Okay, so that's the dipole, or this being the pure dipole. So it turns out that for most materials, at least for small applied electric fields, the dipole that's induced in atoms in the material is proportional to the electric field that's applied. And so the stronger the electric field you put on, the more the material polarizes, that is, separates its internal charge. And the proportionality constant is usually written alpha. You can see a few alphas here. Here's hydrogen, helium, which is pretty small. Lithium is quite large. Beryllium, carbon, neon quite small. Sodium quite large. Argon small. Potassium quite large. Cesium quite large. There is a pattern here, not an exact pattern, but lithium and sodium and potassium and cesium, at least the first three, I believe the cesium, all have one valence electron. So it has one electron which is particularly vulnerable to being moved by an electric field. So we're going to take a look first at a simple model for polarization. A simple model for an atom consists of just a point nucleus and a uniformly charged spherical cloud of radius a. Okay. Now we know that in fact there are atomic orbitals and so forth, but this is just a simple classical model for an atom. So how would we calculate the polarizability, this quantity alpha, of this atom? Well, if we apply an electric field, then it's going to shift the nucleus, the positively charged nucleus, over to the right by a distance d, and it's going to shift the relative to the negative electron cloud. Actually, it'll shift the nucleus over, it'll shift the electron cloud over to the opposite way, but they'll be separated by a distance d. So the external field pushes the nucleus to right, exactly balancing the internal field, and it will push it to the right until the internal field generated by the separation of the electron cloud with the nucleus balances the external electric field. Okay? So it's going to separate it until we reach an equilibrium. And so E is equal to the energy of the electron cloud. And what would the electric field of the electron cloud, sorry. And the field at a distance d from the center of a uniformly charged sphere can be figured out from Gauss's law. I won't go into that derivation right here, but it can be, we can figure that out fairly straightforward way. It's equal to 1/4 pi naught times the charge on the nucleus times d, the distance from the nucleus, over the radius cubed, okay? So notice that if d is equal to a, so we're at the edge, this would just become q over a squared, which would be the field of a point charge, which is what a sphere of charge looks like outside of the sphere, okay? So then, by our definition of an ideal dipole, P, the dipole P is equal to QD, but QD, solving from our equation here for the electric field in this simple model, is equal to, just multiplying through, 4 pi epsilon naught a cubed times the electric field, okay? So we have an expression of the form P, the dipole, is equal to a constant times the electric field. And that means this constant here must be the polarizability. So the atomic polarizability in this simple model is just 4 pi epsilon naught a cubed, or if you write this, write the volume of the atom as 4/3 pi a cubed, we can write this as 3 epsilon naught times the volume of the atom. And so this just predicts that the bigger the atom, the bigger the polarizability will be. And we know that's not true from this table up here. It's too simple because helium and lithium and beryllium, and these are all bigger atoms than hydrogen. And for example, argon is bigger than lithium, but has a much smaller polarizability. So there's a lot more going on here, but it's still worth doing this simple calculation. So it's too simple a model, and in fact, polarization has to be calculated using quantum mechanics and orbital theory. Okay, what about instead of just an atom, a non-symmetric molecule? So when the field is at some angle to the axis of the molecule, so here is a carbon dioxide molecule, if I can find the mouse. There's carbon, oxygen, oxygen. Here is the electric field. What we can do is break up the electric field into a component perpendicular to and a component parallel to the axes, the two axes of the molecule. And then each of them has their own polarizability because they look electrically different. The electrons are lined up, are arranged differently along this axis than along this axis. So the total dipole moment would be the polarizability perpendicular to the axis times this electric field plus the polarizability parallel to the axis times this electric field. Okay, so what about torque? What does electric field actually do to molecules or atoms? Well, molecules really. It turns out that it exerts torque on them. So some molecules, as you know, as we talked about in the last lecture with water, have a built-in permanent dipole moment, just because of the way the electron orbitals are arranged. So for example, water, the electrons cluster around the oxygen, which is negative, and stay away from the hydrogens. So we have a dipole moment pointing straight upward. If the field is uniform, if we put on a uniform electric field, the force on the positive end, so the force on the positive end up here, will be Q, the effective charge Q times E, the electric field, and that's going to cancel the force on the negative end, which would be in the opposite direction. That is, if we have a uniform electric field pointing up, it would exert a force upwards here and downwards here. So there's no net force. However, we do get a net torque. Okay, so here's a picture of this. You can see the positive force here to the right on the positive charge, the force to the left on the negative charge, and those two cancel out. And here's the electric field pointing to the right. But you can see that there's going to be a net effect of these two forces, something like turning a crank, and that is a torque. Okay, so there will be a torque which is given by the radius. So torque is, remember, R cross F. So it would be this radius to this point plus Q cross F plus the radius to the minus charge cross F minus. All right. And then we can write that as the radius to the plus charge is d over 2. And then this force is QE. The radius here is minus the vector d over 2 cross product with QE, with minus QE. And if we rearrange terms here, we find that these negatives cancel, and we just get d over 2 cross QE plus d over 2 cross QE, so Q times d cross E. And so Q times d is the dipole moment, the charge times the separation. So a dipole moment in a uniform electric field E experiences a torque, which is written in our textbook as N, I guess to distinguish it from other variables that use T, like period and so forth, equal to, the torque is equal to the dipole moment cross product with the electric field. Cross product with the electric field. And then finally, this is a fairly brief lecture. The energy of a dipole in an electric field. If we put a dipole in an electric field, it's going to reorient itself. So it's going to reorient so that it points along the electric field. And things tend to move in the direction of decreasing energy. So we can expect that there's a potential energy. And in fact, the potential energy is equal to minus the dipole moment dotted with the electric field. Okay? So let's think about that for a second. So here is the dipole moment, which goes along the diagonal here, dot product with the electric field. So right now those two are nearly aligned, or are somewhat aligned. So P dot E would be positive, and this would be minus P dot E would be negative. Things like to have negative potential energy. So this is heading towards its most favored state. This dipole is heading toward its most favored state, which would be being completely aligned with the electric field, pointing straight across. And just a quick proof of that. So the ideal dipole has 0 and infinity. Its potential is 0 and infinity. The energy of a point charge Q is that charge Q times the potential. So for that dipole, U, the total potential would be Q at the positive charge at the potential V of R plus D, the positive end of the dipole, minus the charge, the negative, so plus the negative charge times the potential at the close end of the dipole. So that's Q of V, factoring out the Q, that's Q of V plus V of R plus D minus V of R, which is equal to Q times minus the integral from R to R plus D of E dot dL, right? Because that's the definition of the electric potential. Okay, so for an ideal dipole, with this integral, the electric field will be constant between the two, and we just get that the integral of this line integral becomes E dot D, okay? Or, I mean, yeah, the line integral becomes E dot D, and the whole term becomes minus Q E dot D. So we just have minus Q E dot D, but then we can just absorb the D into the Q, and we have, because Q times D is charge times distance, which is dipole, we get minus P dot E. Okay, so in this lecture, we've just taken a brief look at the response of materials to electric fields. We've seen that they get polarized. We looked at a simple classical model involving a spherical distribution. We looked at an asymmetrical distribution and saw that there could be polarizabilities along several axes. We saw that dipoles experience torques in electric fields, and we saw that we could assign a potential energy to a dipole in an electric field. All right, great. Thanks a lot for your attention.